one just after lunch. In terms of housekeeping, we've got a fire alarm set at 11:30. So that's the test. If it's any time other than that, then we need to think about evacuating. And we'll do questions after each talk. So to start off, we've got someone from New Zealand. What was the name, sorry? Sahil. Currently not on the call.
Okay.
Cool. So in that case, do we have Suleiman Bello, who can present first? I don't see Donovan in the crowd either. So in that case, yes, we have Anna Scriver from Southampton to be talking about stress-free temperatures. Continuously welded rail tracks.
So, good morning, everybody. My name is Anna. I'm a PhD student at the University of Southampton, and my research is sponsored by Network Rail. And today I will be presenting my paper titled Review of Factors Affecting the Stress-Free Temperature in the Continuously Welded Rail Track. We'll talk about the background and motivations behind my project, and then I will introduce you to the stresses in the rail and stress-free temperature and explain why is it important. And then after I will talk about the factors affecting the stress-free temperature and present some studies from my research, and hopefully at the end I will leave some time if you have any questions. So railway form an indispensable part of our social and economic infrastructure. They play a vital role in and passenger movement across the UK, connecting people and communities. They have a part to play in reducing traffic congestions, pollution, and carbon emissions. Also, rail travel is perhaps the only form of mass, rapid, and long-distance transport realistically offering a carbon zero dioxide emissions at the point of use on the electrified lines. Also, a net zero carbon transport strategy will require a significant modal shift from air and road to the rail. Thus, the rail industry will expect a bigger volume of traffic in the future. Addressing the potential impact of climate change is an essential aspect of current and future railway track management. So climate change increasing the risk of heat waves and floods, which are essential to the railway infrastructure. It is also likely to result in a higher maximum summer temperatures and greater range in the annual temperature. Overall, the weather patterns will become more extreme, causing the more disruption on the railway network. So disruption can be caused due to the rail breaks, track buckles, signal failures, and damage to the track bed, such as the ballast wash out during the floods. And the disruptions can cause, can endanger life and cause the damage that are costly to repair. So to mitigate the future risks, the resilience of the railway infrastructure to the expected climate change needs to be improved. In recent decades, much work has been done to improve our understanding and ability to manage the rail stress, and yet it continues to be a concern for many companies worldwide. So my research is concentrating on the management of the rail stress with climate change for the continuously welded rail track. So let me introduce you to the stresses in the rail. So as we all know, the rail made of steel, and due to the steel material properties, the rail tend to expand longitudinally when And steel rail sections were traditionally connected by bolted joints, as you can see on the top of the slide. And this discontinuity of the rail surface at the joints between each bolted sections produces the high dynamic impact loads on the rail ends, the ballast and the subgrade. And this accelerates the rail failure, sleeper wear, and disruption of the ballast at the joints. So with time, continuously welded rail was introduced to eliminate these issues. So instead of the connected two rail sections with the joints and leave the expansion gap between them, the engineers decided to weld long sections of the rail. This, of course, eliminated the issues associated with the jointed rail truck, but they brought up a new issue, which is the buildup of no gap in between of steel sections anymore. So to better understand this, I produced some figures. So in the first figure, you can see that, I will show it here. We have the steel beam fully fixed on one end and 3 an hour. So it's to represent the jointed railway truck. So when the temperatures increases, it can contract in the same way as well, and the structure will not be disturbed. But for the continuously welded rail, as there is no expansion gap, we have to represent it as a steel beam fixed on both ends. So when the rails hit it, the temperature compression forces will build up, and thus the beam will buckle. So to manage the range of temperature the rail can withstand without buckling or breaking, the stress-free temperature was introduced. So what is the stress-free temperature? Stress-free temperature is the temperature the rail is passing to the slippers without the creation of the stresses. It can also be called installation temperature. In the UK, it is at 27 degrees Celsius. So as you can see in the diagram, while the rail temperature remains below the stress-free temperature, the rail will be in tension. And as the rail temperature rises above the stress-free temperature, internal compressive stresses begin to develop. So large internal tensile or compressive forces can lead to the rail breaks or truck buckles. And it can happen when the internal forces are sufficient to overcome either the local tensile strength of the rail or the lateral restraint to the buckling provided by the track system. Also, the stress-free temperature is used to determine rail temperature, and the critical rail temperature is the temperature of the measures to protect the traffic must be taken, and usually it is the speed restrictions. So however, it is not easy to measure the actual stress-free temperature in the rail, as the measurement techniques are generally difficult to deploy. Thus, it is important to understand the factors affecting the stress-free temperature so it can be easily estimated and the correct critical rail temperature can be assigned to prevent any accidents. So one part of my research is to investigate the factors affecting the stress-free temperature. And also, apart of the obvious factors which affect the stress-free temperature, such as inadequate stress restoration following the maintenance procedures and disturbance to the rail, I've identified 4 less known factors, and I will present them now. So first factor is the longitudinal restraint to the rail movement. And longitudinal resistance provided by the fastening system and the ballast. And if either of them, the clamping force of the fastenings or the ballast condition is poor, the shift, and thus the stress-free temperature will be affected permanently. And the second factor is the rail temperature change. So daily and seasonal variation in the temperature. If there is a slip at some clips, but not others, the residual stress following the multiple cycles of differential heating and cooling could vary along the length of the rail, and thus the longitudinal movement. The rail temperature can change with the daily change of the temperature. So on the track location, so a part of the track located, let's say, on the sun and part in the shade. And if the fastening system is not hot part of the rail to the part of the rail in the shade, and the stress. So the third factor is the longitudinal acceleration forces. So these forces also requires the inadequate condition of the fastening for you to permanently affect the stress-free temperature. There is differential track settlements. As you can see in this picture, the differential track settlements, they change the vertical of the rail, and thus there is a local variation in strain, and hence so this factor does not require any other conditions as the poor fastenings or the ballast. So it can affect the stress-free temperature permanently. I decided to have a closer look at track settlements. And as I said before, due to this track settlements, the rail tends to bend vertically to fill in the gap in the ground. So we can say what differential track settlements it increases the length of the rail, and increase in the rail length will result in the increase in the rail tension. And calculating the arc length of the new deformed shape, we can identify the rail in the rail sections and find out the change in the stress-free temperature. So that's what I've done. I created some MATLAB code to upon all the points what I talked about, and we've got a graph, and you can see that the change in stress-free temperature is increasing with the ratio of misalignment magnitude to the wavelength, and that was the first study of my research. And just to conclude the presentation, traffic in the future, and it is essential to make understand and mitigate the factors affecting the development of the stress-free temperature in the continuous loop using the finite element analysis and numerical.
Thank you very much, Anna. Do we have any questions from the audience? Andy, I thought you might.
Yeah, I thought so as well.
Thanks. Yeah, really interesting.
Thank you.
My question is, in overhead line electrified areas, the running rail is often used as a return conductor for the electric current. Have you looked or are planning to look at whether that affects the temperature of the rail and hence the stress features of it?
Yes, thank you for the question. And my answer is no, because I'm looking at the structural analysis of the railway and more how the track settlements can affect it. And yes, I will not be looking at that. Sorry.
That's fine.
Maybe in the future I will do my postdoc on it.
I think the lady from the family also had a question.
Thanks for a really interesting talk as well. I know nothing about this. So the question is, how do they cope in hotter countries? So for example, I know in parts of China, they have very high speed rail networks, but they have much hotter summer temperatures. Do they have a different way of laying the track? I mean, what do they do basically?
Yeah. So if I can I go back? Yeah, so as I say, we have something called stress-free temperature of the rail. So it's basically when the new truck is built up or after the maintenance, the engineers come and they stress the rail to the temperature of 27 degrees in UK. So at this temperature, the rail has no stresses. So the stresses is zero. So in other parts of the world, for example, in China, where the temperatures is higher, the stress-free temperature is probably going to be higher because they don't experience the low temperatures. But for the UK, it has to be 27 degrees because in the winter we do have a low temperatures. And if our stress-free temperature will be higher, in winter we will experience the truck buckles. So sorry, the rail brakes. And yeah, it might reduce the truck buckles in summer, but it will be dangerous for the trains to move in winter then. In some countries also, they re-stress the rails. For example, if they have really hot summers and they're really hot, cold winters, they do re-stressing of some parts of the rails, but it is expensive, and in UK they don't want to do it, and there is no point of doing it because our temperature variation is not that big. Yeah, so we don't have like -40 and +50s. So for now, the stress-free temperature is 27 degrees, but it's also part of my research to look into if we need to increase it for a few degrees, or we can just leave it like this and do some re-stress months. But yeah, for now, I hope I answer your question. Thank you.
Thanks. Just in terms of defining that stress-free temperature as 27, how do they do that then? Is that?
I think they just sat down and decided.
Well, there's not a pre-intention that would help them define that as 27 degrees.
When they do the stressing.
Yeah, what we are actually laying it.
Oh yeah, so they do. They do have some equipment which tells the stress-free temperature. Yeah, when they're laying the rail, it is 27 degrees, but with time it varies. So they actually have some sort of like a table where they have to reduce the stress-free temperature by 3 degrees every year. Yeah, because they just assume, because it's expensive to check the actual stress-free temperature after laying of the truck, because there is no non-destructive, so we have to close the rail, the line, we have to lift the rail, measure the strain, and then the temperature. Yeah, so it's actually to create some method which we can just measure it, not closing the lines and stuff. But they do know it when they lay the new rails. They do measure it. But it's 27 degrees, but it can change in a few days or in a few months. No one knows how to, because you cannot visualize it.
Do we have any more questions from the audience?
Yeah, again, I don't know that much about it, but in terms of, so I can imagine compressive failure in terms of basically, tensile failure. Is tensile failure a lower risk for these tracks? And in that case, could it be sensible if you're upping the stress-free temperature, you'd be increasing the risk, I guess, of tensile failure, but reducing the risk of compressive. Is that something? I know for concrete, for concrete, you want to keep compressive. You want to keep the force in compressive because you can control that better. Compressive failure is not as big an issue. Is it the reverse? Don't know if there's any structure to that question.
No, that's fine. So yeah, when there is a tension stress in the rail, rail breaks.
Yeah.
So when there is a broken rail, we still have to close the truck, and
So
we
it's
still have to repair it immediately. You cannot go on the broken rail, basically. So that's why this issue is like hard to mitigate, because it needs to be in the middle. It cannot break, or it cannot buckle. So
Okay, yeah, no, that
you
makes-
cannot just let something go.
So it is an optimization, it's trying to
Yeah.
work, which is what I guess we were saying, it's trying to work out the exact
Yeah,
like
right.
sweet spot for
Yeah.
the climate, but like the question about China, that makes
Yeah.
sense. Yeah,
Yeah.
okay, that's great.
Yeah,
Thank you.
so in every country is different
Yeah.
because of the climate.
That makes sense. Thank you, I really enjoyed
Thank
it.
you.
So hi Ed, do we have anyone online?
Yes.
So we have Sahil Maseni from New Zealand talking about sizing multi-day batteries for renewably driven microgrids. Yes.
Hi everyone, can you hear me all right?
Hi, Sahil, yeah, so we're just pulling you up on the screen. Are you sharing your screen now? Is that Sahil sharing?
Yes, I'm trying to share my screen, and unfortunately, I cannot, open my video because it says it's not allowed. I don't have access.
Technology a second. We can see your PowerPoint though, so that's a good start.
Can you see it now?
Yeah, so PowerPoint's good. We can't see you personally.
Yep. I cannot start video. Here we go. Right. Hi everyone. I'm glad to be here today talking about the multi-day battery dispatching to improve the economic viability of renewables-driven microgrids. So I'm based in New Zealand, and I'm really glad to have the opportunity to present my research today. So I will first briefly introduce the problem, and then we'll go to present the methodology and briefly present the test case microgrid system to which the methodology is applied, and then I will present and discuss the results before drawing conclusions and recommending areas for future work. So the optimal microgrid sizing problem is important as it ensures the best use of really limited resources. And the optimal microgrid sizing methods can be generally categorized as mathematical optimization based or meta-heuristic based approaches. And the dispatch strategies that are commonly used in the microgrid sizing methods can be broadly classified into rule-based approaches or optimization-based algorithms. Now, integrating a multi-day linear programming-based energy scheduling approach into the standard meta-heuristic-based microgrid sizing processes has the potential to minimize the associated simulation to reality gaps. So the wider literature around the optimization algorithms applied to the microgrid sizing problem, like I said, can be broadly classified into exact mathematical optimization-based algorithms, such as the direct algorithm, linear programming, mixed programming, and mixed nonlinear programming. These algorithms are really fast, but they're associated with several simplifications of the problem, and therefore they cannot be relied on. So meta-heuristics are recently increasingly being used as an alternative to exact mathematical optimization algorithms. These algorithms have the potential to see the non-simplified design or search space of the problem. And the notable examples of meta-heuristics or AI-based optimization algorithms are genetic algorithm, particle storm optimization, artificial bee colony, and so forth. And the overall meta-heuristic-based microgrid sizing methods flowchart is shown in this diagram. So first, all input data, such as including the techno-economic specifications of the candidate technologies and the forecasted hourly climatological or meteorological and demand and wholesale electricity prices, as well as the project lifetime and real interest rate are loaded in the model. And the optimal sizing procedure is then starts by minimizing the objective function, which is the total net present cost function, subject to several technical and operational constraints, including the reliability constraints and the set points of the components. And these iterations continue until all the constraints of the problem are met. And that gives us the least cost solution set of the optimal sizes of the components, and as well as the associated total net present cost of the project and the cost optimal sizes of the components. Now, unlike the the mainstream approach that is currently used in the those meta-heuristic based microgrid sizing methods, in terms of the dispatching dispatching and scheduling of the components, which is commonly a rule-based algorithm where we have a greedy cycle charging algorithm. What we've proposed is to use linear programming based forward-looking dispatcher strategy over a moving 24-hour horizon. So in this dispatch strategy that is integrated into that overall meta-heuristic based microgrid sizing flowchart that I've just shown you, we have divided the year-long operation of the system into daily sub-horizons. And in each of those daily sub-horizons, we minimize the operational cost function. And this optimization algorithm or problem is solved over on a daily basis at each at an hourly resolution, subject to several operational level constraints. And this continues until we have the optimal schedules of the components for the entire year. So this is the test case microgrid that we've formulated to test the effectiveness and utility of this microgrid sizing method. So we have solar panels and wind turbines as the primary generation sources, and the storage. We have lithium-ion battery storage, and also the microgrid is a grid-connected one. So we can have power exchanges with the wider utility network. But unlike the cycle charging scheduling strategy, here all those power exchanges and the schedules decision are based on optimization rather than predefined rules. And as a test case, we've use the conceptualized test microgrid for a residential subdivision in New Zealand and in the North Island. And so the residential subdivision is an 8-lot subdivision, and so we have used that test case microgrid system to provide a reliable, affordable, clean electricity generation system for the community residing in the Tutara Bank Eco Village. So we have 8 freeholding lots and a communal building in this case study. And here are the time series input data for this case study. So we have the monthly, mean, daily profiles for a total load demand. As you can see here, the load demand is not very high. It's a small subdivision. And this is the solar radiance. So we are in the southern hemisphere, and as you can see, it's opposite to the solar radiance in the northern hemisphere, and similar with the temperature. And this is also the profile for wind speed, and also wholesale power prices. This is a grid connected microgrid, and we have power exchanges with a wider utility network. So to test the potential of the proposed method when applied to the case study, for that, based on that, conceptualized microgrid system, we benchmarked the results of the multi-day, scheduling with 1-day scheduling, and also the cycle charting strategy. And as we can see here, if we perform multi-day scheduling, the total net present cost of the system is lower than when we perform 1-day scheduling, and also lower than when we perform cycle charting strategy. And this is because of the insight that we have over the future dynamics of the system in terms of the changes in load demand, and also the power prices, and also the future developments of the or future changes in climatic conditions. And here, this slide shows the hourly variations of the battery state of charge. And here we can see that the changes in the state of charge of the battery is lower during the peak hours. We have during the morning peak hours, and also during the evening peak hours. And this is because at those hours, mainly the power is, the solution algorithm decided to, import the peaks, the peak load demand, then overbuilding the generation assets, and also it also didn't decide to allocate a large battery capacity, and this is why the delta SOC is much lower during the peak hours compared to the other hours compared to the off-peak hours. So as conclusions, we have devised a novel design and dispatch co-optimization modeling framework for grid-connected, battery-supported, renewables-driven microgrids. And we have shown that a look-ahead multi-day optimal energy management is a useful approach for designing cost-of microgrids that integrate energy storage devices with appropriate operational timescales. And as future work, we have planned to integrate demand-side flexibility resources into the proposed co-optimization framework, and also we have plan to characterize various sources of data uncertainty, such as the uncertainties in forecasts of load demand, meteorological data, and wholesale power prices, to make the results more realistic and so that they can better represent reality. Thank you very much for your attention, and I'm happy to take on any questions you might have.
Thank you very much, Sahil.
Morning, Sahil. I just wanted to ask, in terms of the forward look and the data you used, was the data that you used to train or determine the ratings of the system then the data that you actually used for the simulations?
Actually, they were used for the the simulations, during the simulations, and no pre-processing of the data was conducted, if I could understand you correctly.
Yeah, so you're looking at a forward-looking system. So is the data that you're using already in existence?
Yeah.
Or does it? Right, okay. Okay,
Yeah.
thank you.
Sorry, I can't hear you if you have any questions. Oh, yeah.
Yeah, sorry, can you hear me now?
Yeah, I can hear you now.
Hi, sorry. Yeah, I had a question about like sort of New Zealand society and structure in terms of like with the UK, we've got quite lots of sort of built up villages. So like microgrids might not be sort of the first port of call when it comes to electrical sort of transference and all that. So what about New Zealand? You mentioned Tarabank in your case study. Is there more scope for sort of areas like these?
Yes, and the main reason for why we went with the microgrid solution for this community actually was, the network congestion, and the network is really congested at the area of the study, and they have outages. They experience outages during the winter high season. And therefore, they place, and also they place a high value for, a reliable supply. And, actually, their energy bills will be increased when the microgrid is implemented. But during the, based on a questionnaire, we identified that the community is totally happy with that. And also more broadly in New Zealand, there are other places with other drivers for microgrids. For example, in the there are several islands that are not connected to the mainland power system, and they are using diesel-based generators for communities of up to 400 to 500 people. And so in the mainland New Zealand, the drivers are mostly related to the network congestion, but there are also many islands that are currently mainly supplied by diesel gensets.
One final question for me, because I used to live in New Zealand. I was just wondering how the Maoris and the Maori communities have they so Tarabank and Maori community, how are they sort of accepting this new style of thing? Are they got any opinions or anything like that you've found?
Unfortunately, I don't have, I wasn't really exposed to Maori community, But for the Total Bank, but based on a little experience that I had over the last couple of days that I was living in New Zealand, I'm originally from Iran. I came to pursue my PhD here in New Zealand, and I really don't know. I don't think I'm aware enough about that. Sorry.
No worries. Thank you very much. Do we have any more last questions, or should we move on? All right. Thank you very much, Sahil.
Thank you.
We have Suleiman on the call for the next speaker. He's in person. So yeah, welcoming Suleiman to the stage for the next talk, introducing perovskite solar cells and their characterization.
Is it?
Raise the points at the top and then these two change.
Hello, everyone. As you know, my name is Suleiman Bello, a PhD student in the Chemical and Biological Engineering Department at the University of Sheffield. My research interest was to investigate perovskite materials for solar cell production with improved stability and high efficiency. Today, my presentation is Introduction to Understanding Perovskite Solar Cell and their Characterization. This work was jointly conducted by Francesco, Adams, and of course myself, which was supervised by Dr. Alan and Dr. Ali. Our aim was to establish a basic guide to the studies of perovskite solar cell. So, just a quick overview of my presentation. In my first few slides, as introduction, I would like to talk about the potentials of solar energy, then photovoltaic technology, and then the photovoltaic effect. While in the second slide, it's all about the solar cells working principles. And then the next few slides just based on the properties of perovskite solar cell, and then fabrication of perovskite solar cell, and lastly, the characterization of the perovskite solar cell. So, there's an image that illustrates how the Earth receives photon energy from the sunlight. It was actually obtained from strascos.com. So as you can see, the Earth actually receives a photon energy from the sunlight. But actually, the angle of the sunlight actually influences the amount of energy that's been received by the Earth. But based on the data that was released recently by Solar Energy Explained Science, they claim that actually the Earth received about 173,000 terawatts of photon energy every hour. And before the COVID-19 lockdown, the total world energy consumption is around 160,000 terawatts, which means the use of photon energy to generate electric power is a promising technology. And this has actually motivated research scientists to go into renewable energy for the production of electricity, such as using wind energy, solar photovoltaic, or hydroelectric power. So actually, what makes this technology an effective way of generating electricity, basically it's just based on the photovoltaic effect. When we say photovoltaic effect, what is photovoltaic effect? Generally speaking, photovoltaic effect is just like a release of electron from a conducting material. This conducting material can be a metal or a semiconductor. So this is just an illustration of an image of a conducting material. Based on the quantum mechanics theory, it is claimed that all conducting material has electrons in them, which move randomly. And when they absorb sufficient photon energy, the electrons in them try to escape. So you can see when the photon energy hits a moving electron within a conducting material, after absorbing sufficient photon energy from external source, they try to escape. And this allows the possibility of harnessing this electron to produce electricity. But actually, most of this photovoltaic technology, they actually use semiconductor as the absorbing materials, because it has a few nanometers separate between the conduction layer and the exciting state, which allows the possibility of harnessing or extracting the electrons from the material. Photovoltaic actually is being categorized into 3 working principles. We have photovoltaic that works based on p-n junction, and we have photovoltaics that works based on excitonic principles, and we also have photovoltaic that works based on pin junction. So p-n junction is basically made of materials it's made of inorganic materials such as silicon, germanium, cadmium telluride. And how do they work? Actually, they work based on a semiconductor that is partially doped with either a boron or a phosphorus to create an N-type semiconductor and P-type semiconductor. Well, for organic materials, they were actually made of excitonic materials. That means the absorption, when you say we have the organic material, sorry for this, the organic photovoltaic is made of excitonic materials, which means the electrons in them is being combined together. That is, you have your electrons and hole being attached together, which could be explained from here. You can see you have your electrons and hole together, and this requires a separate material in order to separate the two electrons. That is, to separate this exciton, you need an electron acceptor and an electrode donor. Well, here, this one is also a dye-synthesized solar cell. It's also known as excitonic method of generating electricity. And this actually uses mesoporous nanoparticles made of titanium oxide, which is being coated using ruthenium, which is made of ruthenium polypyridine, ruthenium polypyridine, to create where you have your electrons here. And when they absorb a photon energy, the electron within them try to escape to generate electricity. And electrolytes made of iodine, which try to refill the photons nanoparticles there. So a perovskite architecture. Actually, perovskite solar cells are being made either using an inverted method or a regular method, or using my mesoporous substrate. And the way it actually works, like the perovskite absorbing layer, and it tries to create an electrons and a hole where they try to separate using electron separation, and then a hole separating layer. So perovskite is made of naturally it's made of calcium titanium oxide, But actually perovskite nowadays can be synthesized using other materials such as methyl ammonium sulfate. So this is just a structural illustration of how perovskite looks like. So you have your you can see from here, this is the general formula of perovskite. We have APX, which this 2A is made of cations, and then this X is made of anions, mostly halide. Yes, mostly halide made of iodine, fluorine, and bromine. So perovskite materials are normally made, are tunable. They have high absorption. They are so good in so many things. This is just a formula that illustrates how to determine the structure, the stability, how to determine the stability of your perovskite materials. How do we fabricate perovskite solar cell? Actually, perovskite can be fabricated by different methods. We have this spray coating, we have the spin coating, and we have injecting, and we have slide dim coating. But most of the time in laboratory fabrication, most of the time we use spin coating to fabricate perovskite solar cell. And why do we use spin coating? Actually, because it's the easiest and faster way of producing perovskite in a very short period of time. So how do we spin coat perovskite using spin coating machine? Basically, this can be done either by introducing anti-solvent or by directly just coating, fabricating your perovskite material. So by directly spin coat our perovskite on a glass substrate and then annealing for some time to create a perovskite crystal surface. Or we can also introduce an anti-solvent during spin coating. Here you can see we have anti-solvent to produce a perovskite surface. And then finally, we can just go through using two methods. Actually, as I explained initially, the perovskite is made of two cations and anions. So the first cations mostly is made of methyl ammonium, which from here you have your second cation is made of lead iodide. So if you have your lead iodide as your first cations, and then second on, you went on and put your second organic material made of methyl ammonium, and then you anneal it to give you your perovskite surface. How do these crystalline form? How do they form after you have spin coat your perovskite solution on a substrate? Basically, we tried to emulate the Vollmer-Weber coated method, which shows how the perovskite try to transform after a certain period of time. So this is just how the crystallization moving from at initial when the solution is being coated on a substrate, the concentration tries to increase, and it reaches the maximum concentration to result to the formation of perovskite crystal surface. Well, one of the disadvantages of perovskite is their degradation. So they tend to degrade easily if they are not well packed. So most of the time, some people try to use a separate glass substrate to encapsulate the surface so that they can stay for some long period of time. Our results, where we try to use UVVs to characterize our materials. Actually, the aim of using UVVs, we tried to determine the band gap of the of our perovskite materials. And in doing that, you can either use a direct method, just to use this formula of light and your Planck constant, and this wavelength is mostly obtained from this edge. When you extrapolate from here, you get your wavelength, and then you do a direct calculation for you to have your band gap, which is the most easiest way to determine the band gap of a perovskite material. And another way a band gap can be determined using a chalk model. A chalk model is the most accurate that allows you to determine the band gap of a perovskite surface. Actually, if we try to use the chalk model, we notice that actually in our first calculation, we determined the band gap to be around 1.6 electron volts. But when we try to use chalk model to determine the band gap, we got 1.55 electron volt. Although the difference is not much, but this allows you to accurately know the difference, the band gap of a perovskite that is being produced. Of determining the properties of perovskite is by using scanning electron microscopy. This is just an image of some of our results that we use scanning electron microscopy to determine the surface morphology of our sample. So here is just a reference sample of MAPI, that's methyl ammonium lead iodide. And you could see they are well arranged with a very large grain. But when we put in zinc chloride as an additive to see how it improved the surface, we realize that actually the surface tends to change. You can see the surface here tries to change with very tiny grains. And actually, in comparing an image using SEM, is very important to know that, to know the magnification of the image that is being compared. Because once the magnification tries to change, what you are actually seeing tends to differ due to the magnification, which could be seen from here. These two results, we try to manipulate, we try to change the magnification of this lens. We try to see a little bit different image. So X-ray diffractions that illustrate some of our results. This result was obtained from one of my colleagues, Francesco, and he tries to use a wide angle scattering to illustrate, to try to determine the difference between the materials that is being used. And then finally, this is just a solar perovskite thin film. This is just a IV. Yes, this is just an IV curve that illustrates how the and then open circuit voltage is being generated using solar simulator. Actually, this solar simulator gives all the results, because after you have made your solar cell in the laboratory and then you try using solar simulator, it gives all the results. But to accurately determine the efficiency of the solar cell is also advisable for someone to try and make the calculation manually. I hope we have explained some of the parameters that is required to investigate when trying to investigate perovskite solar cell. Thank you. I would like to thank the organizer of this program and the university for hosting the program. Thank you very much.
Thank you very much, Suleiman. Do we have any questions from the audience, please? Petra.
So I was going to ask about your zinc chloride addition. So what were you hoping was going to happen? Because you said it changed the crystallite size. Were you hoping to get zinc incorporation at the B site, or were you trying to modify the interface? So I was kind of interested in what you were trying to do.
Actually, what motivated us to look into zinc chloride, because we were able to read a previous paper that was published that zinc chloride actually improved the stability of a perovskite solar cell. So our aim was to use the same zinc chloride in air in a room temperature. Are we going to see the same result? Because the initial result that was published in the paper, it was being done in a glove box, that is in a controlled environment. So our target was, can we still get the same result if we use it in an open environment? That is our aim target. So already we know that actually zinc chloride influences the performance of the perovskite material.
So at what stage do you add the zinc? Do you add it to the spin coating mixture or do you add it afterwards?
Actually, it was added into the solution of the perovskite materials. Yeah. So we make a perovskite solution of methyl ammonium lead iodide and then try to put in some percentage of zinc chloride into the solution before we spin coat it.
Thank you.
Thank you.
Thank you. Do we have any more questions from the audience, please? Well, thank you very much, Suleiman. Last talker this morning's session before the break is Donovan Aguiar Dominguez, who will be discussing the possibility of using vehicle-to-grid techniques to start the grid back from a black start.
Hello everyone, my name is Donovan Aguilar Dominguez. I'm going to introduce. I'm going to talk about exploring the possibility to provide black start services by using vehicle to grid. About that. Now, Black Star, also known as restoration services, is one of the ancillary services that the National Grid needs to procure to keep the lights on in case of a shutdown. Traditionally, the provision of this service is procured by large power stations. However, as we know, the energy landscape is changing and these power stations are planned to stop in the upcoming years. Some of these power stations. Luckily, the increase of renewable generation and distributed energy resources has opened the exploration of new, as they call in the National Grid, non-traditional technologies to provide this service. Currently, I didn't write it there, but currently the requirements to provide a Black Star are quite strict. They ask you a lot, but this is assumed using non-traditional technologies. It's assumed that new providers, they will not need to meet all the requirements to be able to provide this service. With that being said, in recent reports, technologies such as battery energy storage and electric vehicles have been explored as one of those, some of those non-traditional technologies. Also in these reports, for these two technologies, two main challenges have been found. One is the resource availability of the state of charge at the time of shutdown, and particularly for EVs, their availability during the day. Now, how can an EV support or connect to the National Grid to provide a service? Before that, a little bit of background of this technology. There is this technology called smart charging. This technology allows the EV to charge when the electricity prices are low and, or when the demand is too high, so it reduces the demand on the electricity grid. With that, it also provides the benefit of the owner to reduce the electricity bill. Now, with V2G, it has all the benefits of smart charging, but it also connects and sends energy back to the National Grid. This energy can be sold and they get some money depending on the amount of energy that they give back. Now, type of V2G use, it's called vehicle to home. This technology allows the owner to give back energy from the EV to their house, reducing even further their electricity bill during the week. Also, it includes all the benefits of smart charging of V2G and V2G as well. Now, for this study, we asked a few questions about if they can provide the service or not. The first question is, can we predict the availability of EVs to provide V2G, V2H services? The second question is, can we reduce the consumer's electricity bill by providing these services? Also, what is the EV's minimum SOC available at all times during a week? Also, does PV ownership have any impact on the results? And do energy tariff prices have an impact on the results? We're going to find out in a bit. For this, we developed a machine learning model using the data from the National Travel Survey, which is data collected from the UK government that collects data on how, why, when, and where people travel in Great Britain. This data that we use, it's from 2002 to 2019 with around 5 million records. From these 5 million records, only around 2.2 million people are reported as private car owners. Then, from this data, we split the data in two data sets. One, to predict the start location of the EV with around 1 million records. Then we split in 70% training set, 30% training set. And the same happened to the second data set, but in this second data set, we are trying to predict the end location. Now, this machine learning model, it's a classification model in both cases. For this model, we use light GBM, light gradient boosted machine, if I'm not wrong. And we aim to predict 3 different locations: when the EV is at home, when the EV is at work, and otherwise. So those 3 locations. As you can see on the picture, just right over here, we use historic data, the NTS data. We created machine learning, well, we use the machine learning model, in this case, like GBM, and we develop a prediction model. Now, with this model, we use, as the picture shows, new data. We fed that data into the prediction model, and then we got some predictions. This new data is EV trip data collected by this company on the screen. EI Technology, I forgot the name, in 2015 in England. So this is real world data. After cleaning the data and everything, we got 170 unique profiles, and then we took 50 profiles as a sample. Now, for the optimization model, we created an optimization model with the objective of minimizing the consumer's electricity bill and maximizing the minimum SOC at all times for all EVs. This model was formulated in Python using the Pyomo framework, and we use Groovy as the solver for this model. Also, we took 4 different weeks, which are representative of the 4 seasons of the year, winter, spring, autumn, and summer. In the case of the EV data, we consider the characteristic, the specifications of the Nissan Leaf 2018, which has 30% kilowatt hour battery capacity. And we consider the usable battery capacity for V2G or V2H around 5% or 95%, between 5% and 95%. We use a bidirectional charger, V2G ready, of 7.4 kilowatt power, only charging when the EV, of course, is at home. And also we use a 50 kilowatt street charger when the EV is not at home or at work, just in case if they need to charge even further to use during the day. In the case of the electricity demand, we use real world data collected by the City of London. After cleaning the data, we got 430 unique houses around with an average consumption of around 4,000 kilowatt hour per year, as the UK said on their website. That's the average consumption. And we use 4 different tariffs, all of them supplied by the same company. This case is Octopus Energy. The name of these tariffs are Agile Tariff, which follows the wholesale tariff. The next one is Agile Go, which provides cheap electricity during the night, during 4 hours, and the rest of the day at higher price. Economy 7, which you might be familiar with this one. In this case, 7 hours of cheap electricity, and the flat tariff, which is the same price at all times. For the PV generation readings, again, is real world data collected by City of London. And in this case, the houses have a 3.5 kilowatt PV system, and we consider different PV ownerships from 0%, 10%, 25%, 50%, 75%, 90%, 100%. And we also consider, in case if they want to sell surplus and generation, we consider the Energy Agile outgoing tariff, which also follows, it's like 10% of the price of the Agile tariff, but in this case, they sell that energy. This is an overview of the tariff prices for a week and winter from January 12 to January 19. You can see the variation of the prices. You can see at the top, the street charge is 30 pence per kilowatt hour. This one is the flat one. This one is the Agile Go. Economy 7, Agile, and Agile outgoing. This is an overview of all the 50 houses, showing the mean electricity consumption with the dark blue, all the way same for the same week in winter, January 12, January 19, showing the aggregated maximum of all the houses, of just one house, the maximum consumption of all the houses, so 50 houses, and the minimum consumption, and the PV generation in yellow, orange color. Now the results. For the machine learning model, you are looking at the confusion metrics. These confusion metrics show the true positives, the true positive ratio of the classification model of each label, in this case, home, other, and work. On the left, on the y-axis, you can see the true label, and the x-axis, you can see the predicted label. On the left-hand side, the start location model, and on the right-hand side, the end location model. As you can see on the diagonal, the models have a precision of over 82% in both cases, and an overall accuracy of 85% on the start location for the start location model, and 86%, around 87% for the end location. And now this is how the location was predicted for the availability of EVs when they are home, the number of EVs that they are at home during a week in winter, same week, January 12, January 19, showing that the model successfully captures the travel patterns, showing like most of the time at night, of course, people are at home, then they go to the job 9 to 5 perhaps, and again, going back, going down, going to the jobs, going back home, and so on and so forth. And Saturday and Sunday on this case, Saturday and Sunday, like you can see that people, perhaps they have different patterns during the weekend. In terms of the electricity cost, I'm going to go quickly on this one. You can see a linear relationship considering the x-axis, the PV rate, considering on the x-axis the PV rate, on the top left, the minimum total cost of all the 50 EVs. On the right-hand side, top right, the average total electricity cost, and at the bottom, the maximum total electricity cost. And you can see the linear relationship going from the PV rate going down as the PV rate is increasing. And yeah, those are the results. In terms of the, oh, it's an extra one. Didn't really, it's the same. In terms of the minimum SOC during the week, you can see that the SOC threshold for all EVs, most of the time follows like a trend of like a semicircle kind of thing. And as well shows that the PV rate does impact the maximum or minimum SOC threshold. And you can see that the minimum at all times, regardless of the tariff, regardless of the week of the year, it's around 25% and a maximum of 50%. So with that being said, the conclusion. In terms of the machine learning model, again, the model successfully captured the travel patterns of the EVs during each week of the year that we tested. In both models, the overall accuracy was above 85%. In terms of total electricity cost, depending on the tariff, depending on the season of the year, the electricity cost can be as low as -8 £, which means that you will get paid for charging, discharge using your EV, your electricity consumption, and as high as £54 per week. In average, you can expect a minimum. Well, in average, you can expect to have a total electricity cost between -£4 and £30. Again, this is, like I said, depending on the season of the year. Flat and economy 7 tariffs return the highest cost when compared to the more dynamic tariffs, Agile and Agile Go. And again, this as well depends on the season of the year. In terms of PV ownership, like I said just before, the PV ownership shows a linear relationship with the total prices. The higher the PV ownership, the lower the total costs are for the EVs. In terms of the minimum SOC percentage for all EVs, like I said, PV ownership does impact the maximum amount of, minimum amount of EV of SOC that all EVs can hold at all times. Perhaps you saw on the previous slide that surprisingly, having a PV ownership of 50% return the highest SOC values, the highest SOC threshold for most of the tariffs during the year. Like I said, in most cases, only one tariff, that's the outlier. In most cases, the minimum SOC for, regardless of the tariff, regardless of the time of the year, it's over 30% at all times for all EVs. Finally, it is important to notice that we didn't consider any incentive for the EVs to hold their SOC, to encourage to keep a certain amount of SOC during the week, which of course might be explored later on. So thank you for listening. And if you have any questions, feel free to ask.
Thank you, Donovan. Does anyone have any questions? Andy?
Thanks, Donovan. So two parts to this question. First part is, you mentioned early on that there might be some technical requirements for Black Start that would be dropped effectively. So can you just discuss what they might be then?
They won't be dropped at all. they would be more flexible in that sense. For example, if I'm not wrong, right now, the power station, they have to provide 300 megawatts, capable of providing 300 megawatts. So that's almost impossible with EVs. So perhaps providing 3 megawatts might be possible. So that's a flexibility on that requirement. It's just an example. Yeah.
Okay, thanks. And the second thing is you showed a graph of the domestic demand, I think it was. So I'm just wondering what yeah, that one. So what resolution of the data that you had for us?
Yeah, the original data, let me just go back up just one, two slides. The original resolution for the house electricity consumption, they collected the data for 30-minute resolution. For the PV generation, they collected the data for 1 hour resolution. But we wanted to capture the randomness nature of EVs traveling. The best for that was to downscale for 1 minute resolution. So in this case, if you come very close, you can see the step by step, or at that distance, perhaps you see just a continuous line. But yeah, house demand was collected 30 minutes, downscaled to 1 minute. PV was 1 hour, downscaled to 1 minute again.
So when you say downscale, what does that mean?
Downscale, well, not sure if that's the actual word. We changed the time step from 1 hour to 1 minute. So we created like oversampling, downsampling. And we...
So if you get 30-minute data,
yeah,
and you're taking that to a 1 minute resolution, then is 30-minute time step, are you stepping in 1 minute intervals then up to that data? Clear on what you've done there.
Yeah, I'm just trying to unravel this, to unravel in my head to explain you properly. What we did is the original data, like I said, is 30 minutes for the house demand. But we consider like the top energy, let's say at 11 in the morning, the consumption is 2 kilowatts. So we converted that energy, 2 kilowatts to the kilowatt hour. And afterwards, we just did a technique, which is not sure if it's actually the word, resample it. We just resample it. So from point A, let's say 11 in the morning is 2 kilowatts, 11:30 is 2.5. So between that time, it's for 1 minute of time to reach the yeah.
Okay, thank you.
Yeah, sorry, my head, it was something else.
Thank you very much. Has anyone got any more questions?
Hi, yeah, really interesting talk. So just on this graph here, I think the concept is really cool of using EVs as a black start, but what do you think could be the impact of, so the government wants to electrify more things, especially within the household. So if household demand increases, let's say double, let's say more people have heat pumps, that kind of thing, what do you think the feasibility of using EVs as a black start would be if there's more demand from the household, therefore reducing the state of charge of an EV?
Well, like I said at the end, we did not consider any incentives. Perhaps introducing incentives can switch the demand and say, well, perhaps it's more profitable for the owner to not to use the energy from the EV to the house, and perhaps just keep the SOC at a certain level because they get paid to keep that amount of SOC at all times, rather than just saying, well, this energy I'm going to use it for my house in order to reduce the electricity. And like I said, the optimization model, perhaps like you heard from the previous speaker from New Zealand, he said that the model aims to decide whether it charges or discharges. So depends on the profits. And because we are aiming to minimize the consumption, the electricity bill, that's why it decides when to charge, when to discharge, and if it's profitable or not.
That's great. Thank you.
Thanks.
Just got a question.
Which is
Yeah.
something that I always wonder about when I see presentations on using cars to kind of download to the grid.
Yeah.
Which is, as I understand it, the batteries are limited, or they tend to degrade with the number of cycles. So if you're using a car battery, you know, to continually kind of top up the grid, or it's being that, you know, drained and recharged, you're actually going to shorten the life of the battery quite substantially. Now, how do you account in your model for homeowners saying, car owners saying, I'm not doing this because it's going to shorten the life of my car by 10 years or something? Do you have that in the model? Does that come into account?
Yeah, I understand your point. Yeah, one of the concerns is that the battery degradation for the EV owners. And this model, we did not consider that. But I would say that recent papers, recent studies believe that at some point in the future, when these technologies are going to be fully spread across the country, the profits are going to be more than the cost of the battery degradation. So at some point. So right now I'm not considering it, but it's something that should be considered right now as the current state is. Perhaps in a couple of years, when the electrification is all the way, maybe that's something that politicians consider to do and pay some more rather than not paying at all. Yeah.
Callum at the back.
Yep.
Can you hear me?
Yes.
Yeah, thanks for the talk. Just kind of feeding on from that point, from your sort of reading and the literature and the news, do you see any sort of any move towards, say, a change of ownership of the car or the battery, if that makes sense? Do you see any schemes possible where the utility companies and the energy companies would actually own or somewhat subsidize the car or the battery, or there'll be some sort of scheme where the owner is compensated for the, say, the degradation of the battery in the vehicle to grid system?
Yeah, thanks for the question. I think that just recently EDF, the energy provider here in the UK, started a pilot scheme that they lent, they own the EVs and they lent it to their employees. So the company gets paid, or the restriction, well, one of the requirements is for them to engage on B2G. So the company gets paid, the owner just enjoys. The owner doesn't get paid. I mean, the user doesn't get paid. The company is the one that gets paid because they are paying towards the EV. They get the profits and they just say, just use the car as you wish, or you need to engage at certain times and you need to park outside the company so we can use that energy with the company or sell it to the grid or something like that while you are working. So yeah, that's one option. Second owners, I haven't read about that. So I'm not sure about that. If, I don't know, I'm using the EV and I sell it to you, I haven't read about what would be the outcome of that. So
Thanks for that.
Yeah.
In the interest of time, we'll call it a day here, and we can speak to Donovan now, and the coffee break for the rest of the day. We will reconvene at 11:30, which I realise is also the fire alarm. So when you hear the fire alarm, you can wait for it to go off, and then you can come back here. But yeah, thank you very much, Donovan, and thank you to all the speakers so far today.
Still a few people outside, but I suppose we should get started. So welcome back. Our first speaker is Andre from the University of Southampton. Yeah, about the performance of hybrid battery energy storage systems.
I'm from the University of Southampton, and I'm going to say right away, I'm going to talk about hybrid battery storage. And well, this work would not have been possible without University of Southampton, GSUSA, the Center for Doctoral Training, and of course, without my supervisor, Andy Sharp, and of course, Peter Stevenson from GSUSA. Right. So, what is this about? Right. We know why we need. I'm going to talk specifically about the GSUSA system and about some data which I've collected over the years, right? So why do we need hybrid battery storage, right? All battery experts, you know that if you take a battery and you connect it in parallel with supercapacitors, let's say, what you do, you improve the lifetime of the battery. Why? Because the battery doesn't like, for example, let's say, sharp discharges, high pulses of power, right? So if you connect the battery with a supercapacitor, let's say, you improve the overall lifetime of the system. But it's showing this. So you can link different technologies together. You can link lead acid with capacitors or supercapacitors. You can link lithium ion with flywheels. I think Andy is doing flywheel and supercapacitor linked together and lithium ion linked together. Multiples of studies about this. The hybrid systems. All right. The second on the peak times. So imagine this is your house, right? 30 days, this is a month, and you have a house needs around 10 kilowatt hours of electricity. This is not realistic, this is just to illustrate my point, right? So let's say almost every day, 90% of the days, you need 10 kilowatt hours from the battery. For the weekend, you need, I don't know, 16 kilowatt hours of battery because you're doing some electric grilling, you do a barbecue or something like that, right? If you will be like the electrical engineer sizing the system for this house, what would you do? You're going to say to your customer, well, buy a battery of 16 kilowatt hours and your problem is solved. Right? That's true, you're done. But actually, it's a little bit oversized, the system. Why? Because you don't actually of 16 kilowatt hours to do 30. And you need a battery of, let's say, 4 kilowatt hours that can do only 4 days. Right? System, right? So you don't actually need a lithium-ion battery. If you multiply this 100 times, that's going to be 3,000 cycles. That's a lithium-ion system, right? You need a battery of 16 kilowatt hours. What you need maybe is a battery of 10 kilowatt hours and a lithium-ion battery of 10 kilowatt hours and another technology that can do 4 kilowatt hours, maybe a lower spec, right? Hopefully that. Right, so with that in mind, I'm going to talk about what we looked at is lithium ion and lead acid, right? Lead acid has some strengths, lithium ion has others, right? Everybody knows lithium ion is very good. It's, you can cycle at 3,000, 4,000 cycles up and down, high discharge efficiency, many advantages, right? Lead acid, all the technology has some advantages, like, for example, abundant raw materials. You can easily recycle lead acid, what you can't do with lithium ion at the moment, right? Actually, there's more lithium ion, lead acid battery connected to the grid compared with lead acid. If you consider all the UPSs and all the batteries connected to the grid, there's more lead acid connected to the grid than lithium ion currently is, right? So I can go on and on and on about this, right? But is that they complement in a way each other. If you have a lead acid battery and you protect it, you discharge it slowly up and down. We can't just discard this technology, which we have invested so much in it, right? We have supply chains, we have factories, we have everything. 99% of lead acid is being recycled, so on and so forth, right? Now, I've said If you have a hybrid system, let's say you have, like I've said, a battery and a capacitor together, if you try to connect it together, well, you can't do it directly, but in reality, what you have, you need, let's say, a battery, a capacitor, or two batteries, and you have these symbols, which are like some DC converters. You can't connect them together, right? You need some DC converters there, right? So that's why you don't, tomorrow, you're not going to see in your Tesla put batteries and supercapacitors together. Although they do the trick and they improve the lifetime of your Tesla, let's say. Why they don't do it? It is because the complexity added to the system, because it had to add DC converters, more controls, more, doesn't make sense, right? Okay, so that's the trick with the hybrid system. But what about this is about the fact that you can actually, these two technologies, you can actually link them together without any power converters in between. That's the key point of my PhD, right? So now we're moving to the GSUSS system. So this system, right? So that system was installed in 2018, I think. It was live, and it's been working ever since. University of Sheffield worked at that time. This project, I guess, linking some wind turbines, PV systems, some GSF factory, some kind of a microgrid together, looking at power flows and so on and so forth. But now that project, I think, is done. So we're only looking at peak shaving with the GSF battery, right? More recently, there have been some more installations of this type. By the way, so this type was the first type, the first of its kind in the UK, right? So, for example, this one went live last year, I think, in Portsmouth Port, very close to Southampton, where I live, right? So, this kind of system, because it offers such a very simplistic solution in fast wind, we have quite a little bit of on the energy storage media about this, which is quite interesting for me to see people being interested in something like that. So this is a GSUSS system, very simple. Batteries connected together. 3 of those are lithium-ion, so these are lithium-ion, and there's a lead-acid thing as well. There are hundreds of cells in series. You can see here the battery specs. So that's not really important. It's a 100 kilowatt system. 2018 up until July, September. I haven't taken the last readings in the last few months, but I'll do that as well. So this is all the data that we have. We have a few gaps in the data because the system was shut down because we had some issues with the inverter. Right, so all of that, this is around 500 to 600 cycles in here, charge-discharge cycles over 3 years or so. It was usually run during the week or during the weekends and so forth. That's not really important, right? So if you're on, this is, right? So if you understand this cycle, you understand everything about this presentation, right? So what do we see in here? The dotted line are the charging bit, and the solid line are discharge bit, right? Starting from there, you can see that the blue line is the current through the lead acid, lithium ion. The red one is from lead acid. The voltage is in black. Up there, you have the state of charges as well. So what you can see when the system is connected, like I've said, directly at the DC link, when you start to charge it, you see lithium ion charging a little bit first. There, that spike over there, the blue spike. Then you see the red coming in, and then they slowly die out, and they reach the state of charge roughly at the same time, right? But you see a few ideas in here. You see this point, for example, right? So that's one of the first points of interest. Once you start charging and you stop at that point, you see some fluctuations between the string because of the different time constants. So, for example, from this point to this point, lead acid string is charging the lead acid, right? Now, within this point, we're starting to discharge, right? This is the fundamental point of this presentation. When you start discharging this system, the first thing that discharges is lead acid, which is counterintuitive why that's the case, right? If you have two batteries connected together, like in high school, and you start discharging, you expect, if you discharge with 10 amps, you expect to be one string, let's say 5, and the other one 5 amps, right? Equal sharing. That's not what happens, right? So the first thing that discharges is lithium ion. That's exactly the case what I was trying to make earlier. If you remember with the base, cover that base, and the top graph, the peaks will be covered by lead acid, right? So in this way, you're cycling up and down lithium. You can do many cycles, and then lead acid covers only the peak times. Lead acid can't do 3,000 cycles. Well, in this case, it does, but just as an illustration, right? So as you start discharging, there is an equal, then lead acid picks up the peaks. And when you stop discharging, that's another thing we looked at. There is a little bit of a spike at the end of it. Basically, what happens is the other way around. So lead acid now. Between the strings, you say that's loss of efficiency, that's not good, and you're probably right. In this case, though, in here, this bit, right? Lithium ion charging the lead acid, right? You can say that's loss of efficiency. Yes, there is a bit of. What do I mean by that? When you're charging the whole system, you have to consider the charge efficiency as well. So the charger in this bit works at 10%, 5% of its rated capacity value. So if you have a 100 kilowatt system, inverter or charger, and it works at 5%, adding the top-up charging here, the efficiency of the inverter is very low, 80%, 85%, right? Usually an inverter, if you buy an inverter or a charger for your house, it's 97%. But it drops to lower values if you're charging it really slowly. So that means what you can do, you can just charge the system at a very it's added from lithium ion to lead acid. Although we don't want that to happen, we can work that. Right, so some of the data, right? We have in here that graph and that graph. What we see there is the values for the cells that the system has been cycled. So a lead acid system was charged between around 1, you see, above 2 to a little bit overcharged, 2.4 to 2.35 or something. So that means it was not discharged completely. So we don't want lead acid to be discharged completely because the lifetime is going to be very low. So this is how the system was operating. Oh, by the way, what we have here, each one of these dots represents a cycle. So I've taken around 140 cycles on that, right? Okay, so that's the lithium ion. So lithium ion from around 3.4 to 4 point something volts. That represents to what? So you can see the system was charged up and down from around 40%, instead of charged to 100 and back to 40. It was not taken from 0 to 100 and back to 0. We don't want the battery, especially lead acid, to be 0%. Lead acid, on the contrary, was cycled differently from around 5, 10, 7% to around 100 and back. Right? Hopefully that gives you an indication of how the system was run. So we have some values in here. So what you can see on that graph is the total discharge energy for each cycle. So the system is around 270 kilowatt hour. We didn't discharge it completely, so we kept it around 210, 200. You can see there, the black one is the total, the black dots are the discharge energy. You can see that in the last few months, it was run at the lower power. That means we had some extra energy because lead acid likes to be discharged at a low, high rate. So we have more energy from that. So that's why we see an increase over there. But you can see that lead acid a little bit more in the last few months. On the contrary, lead acid lithium ion was quite constant, right? Lithium ion doesn't care about the discharge rate. Okay, now, what you can see on this graph, this is the charge fluctuations between the strings, which I've showed you earlier, right? So the brown dots are that's around, you can power your house for a day almost, right? But that's constant over the entire cycles, right? But on the contrary, when you stop whatever the magenta dotted lines are, the transfer from lead acid to lithium ion at the charging rate. Which can be spread depending on where you want to stop, right? Okay. So on this graph, I've shown all the energy discharged or lithium ion discharged before the lead acid left. So like I've told you, you start discharging the system, the first thing that discharges is lead acid, lithium ion, sorry, and then equalization point. So this graph shows the energy discharge from the beginning, to that inflection point over there. Right, so you can see roughly 100% of lithium was discharged before the inflection point. If I remember correctly, the value is around 91%. But nice string of lead acid, of lithium ion. Again, we can cover that entire base with lithium and keep the base for lead acid. I'm going quite fast with this, hopefully it makes sense. Right, so that's these are the conclusions, right? If I work at different voltages, don't do it. Well, we have a system which works. It didn't work for the figures there, which I've talked about already. Around 90% efficiency, some charge transfer between the strings, but that's not really important. The main idea of the presentation is that these two systems can work together. Hopefully that makes sense.
Andre, great talk. So do you see this being widely adopted in the future?
Right, so let's be honest, the vast majority of grid-connected systems are lead acid, lithium ion, right? In terms of the newly added 14, 15, 16 gigawatt hours of lithium at the moment, right? The hybrid system usually are very niche opportunity, but these systems work very well. I mean, all of these systems, even the Portsmouth one, have been used for peak shaving for, let's say you have a car park where you have cars, right? You have a highly irregular load, right? So that means you can do one. That system works perfectly for car parks or like not upgrading the infrastructure. They use it, the Portsmouth sport, that's why they've done it, right? Because they don't want to upgrade all the infrastructure. So it's, why is that? It's because you have a regular load, the peaks covered by lead acid, the base again covered by lithium.
So we should have Solomon. Yeah. Talking about thermal characterization of cylindrical lithium-ion batteries.
I'll be presenting on thermal characterization of 18650 NCA and NFC cylindrical lithium-ion batteries. The overview of my presentation is this. I will cover the background of my studies, and it will tend to answer questions of why do I choose the NCA battery, which is an acronym for lithium-ion, lithium nickel cobalt aluminum oxide, and that of NMC, which is lithium manganese cobalt oxide. And also, why do I choose to look at it in the context of thermal characterization? Why is it important to know their thermal properties? Then I'll proceed to look at, talk about the mechanism of heat wave seek experiment, which is the technique used to conduct this study. And then I'll proceed next to set up, to show the setup of the experiment and the actual procedures I used while conducting the studies. Then, and I will show the results covering the areas highlighted, and then I'll conclude with key findings. We know that lithium-ion battery is very good for storing electric energy in chemical forms and then convert back to electrical energy when needed. Of course, someone at the immediate person who just finished presenting highlighted some of the key properties, which is high energy density, high power density, and they have a long cycle life and many other good attributes that make them attractive and preferred over other kinds of batteries. Yeah, but it still has some challenges, and the two key challenges that I'm focusing on, or that of interest to me regarding this research, is the fact that we continue to demand for higher capacity of batteries. We believe everybody here would love to have his mobile phone or laptop stay a week when charged once, and even the electrical car users desire to have a longer range, driving range when the battery is charged once. So that continue to fuel demand for high capacity batteries. But unfortunately, there is concern around safety of battery, and batteries with high capacities tend to be more thermally unstable. And among those batteries with high capacity is the NMC and the NCA. And that's the reason why I choose to look at the two battery type. Then what am I looking at in this study? I understand that knowledge of thermal characteristics of batteries will be helpful in designing suitable heat management system to keep them under conditions that trigger them into thermal runaway away to keep it within safe temperature limit. So, and when we know this, we know the amount of cooling that will be provided to keep the temperature within the safe range. And that brings down to the aim of this study, which is to determine the thermal characteristics of some commercially available NCA and NMC batteries. So the heat weight mechanism, this is the mechanism I used to carry out the experiment. And what this means is that the batteries will be heated. The battery will be introduced under an environment that is controlled, thermally controlled, and the battery will be heated to certain temperature step, and we wait for a while for it to attain thermal equilibrium with the environment. And then the battery will be observed. You seek observing the battery for some time to know if it is generating heat from within itself. If that is not happening, it will be heated to next step. But if that is happening at this set temperature rate, the system will switch to exotherm mode, under which the system will track the thermal progression of the battery to thermal runaway. So, and when the maximum temperature is attained, the system automatically switches to cooling mode and cools down to, well, that is a completion of the thermal runaway test. And if you look at the right-hand side, yeah, you see a kind of graphical representation of the mechanism. On the top side, you see a step, which is zoomed in here. When the heat is applied on the battery, it increased by this step, which is represented by this change in temperature. And then when it gets to this level, you wait for it to attain equilibrium with the system. And then you seek to observe if there is exotherm. If there is no heat generation from within the battery, then you proceed to the next step and heat. And that's why you have this step proceeding to when thermal onset. That's the point when the battery starts generating heat from itself, from within itself, and the system stopped heating the battery, but rather track the temperature growth of the batteries. Then this is the experimental setup, and let me say here that the way I carried out the study, first of all, I charged the batteries using battery cycler to set a state of charge, and I used marker for that. Then I proceeded to test the batteries in the accelerated rate calorimeter, which I sketched here. On the side, you have the top, you have the side and the bottom. Each of these region has a heating system that can apply heat to the battery, which is situated at the center, chamber, pump chamber. And the thermocouple is connected to the sample to read the temperature. So, and I started the test from 50 degrees Celsius, from literature is clear that thermal runaway occur above this and half is a little lower to track. And the temperature step was 5 degrees, which is small enough to observe, to figure out exactly the point where the battery itself starts heating. And then the wait time was 60 minutes and the seek time was 10 minutes. Then the temperature sensitivity was 0.02 degrees Celsius, 0.02 degrees Celsius per minute. So when the temperature rate of the battery increases to this level, the system switches to exotherm mode and then track the heating of the battery. Then you can see on the lower side, sample of a picture of battery sample in the arc chamber before the test and after the test. So the result, this is a plot of thermal runaway test on NCA at 100% state of charge. And you see the progression, the trend. The green side shows when the battery was not heating itself. That's the heat wait seek period. And then the orange plot shows the region where the battery was heating itself by undergoing decomposition reaction. A lot really happened within this region, and that's why I added this picture to give a kind of a hint of what goes on, because the onset is at the point where the first reaction, exothermic reaction, commences with the battery, and that is decomposition of the solid electrolyte interface, which is a coverage between the anode and the electrolyte, and then it progresses to decomposition of the electrolyte. So all of that happened within this orange region, and then there's a venting here. There is a little drop in temperature. Gas generated from within the battery tend to absorb some heat and then result to a little moment of cooling, and then it proceeds to thermal runaway, which is a speedy reaction that releases a lot of heat and sometimes cause fire, things like that. So this is a zoom in instead of the thermal runaway region. The temperature of the battery increased sharply to the maximum of about 824 degrees Celsius and then cools down. That's a sample of the plot. Then the onset temperature for the test. Each of the tests at a different state of charge. The test was repeated 4 times to know the difference, observe the difference, how the onset vary with cells and whatever. So that's why I have the error bar showing the region, the variation across the batteries. And you see the red plot represent the NMC, and the highest onset temperature was recorded at 0. That means it is most stable at that point. The battery takes longer, endure more heat before undergoing thermal runaway, and that decreased with increase in state of charge to record the highest at 100% state of charge. And the same thing happened for the NCA, which is the black plot. That's that. You can observe here that the lithium, the NMC, really the onset of NMC is mostly low, slightly lower than that of NCA, except for 0.25 degrees state of charge. Probably that's because the capacity of the battery is a little bit higher. It has more energy stored inside of it at the point of the test. Then the maximum temperature attained. The black plot shows the NCA, and the maximum temperature increased with state of charge up to 0.50, where the maximum temperature was already recorded, and then followed an irregular order to the rest. And the same thing happened for NCA. So this indicates that the amount of heat that can be released from battery when they undergo thermal runaway can be as big, as much as it could be at 150. don't know if you understand that. Like at 50 states of charge, battery can really release substantial amount of heat, as much as it could do when it is charged 75 or 80 or anything more. Then the temperature rate, and looking at the effect of state of charge. For the left-hand side, I have the NMC. You can see plot for different state of charge from 0 to 100. And on the plot, you see that the heating rate of the batteries during thermal runaway was increased with a state of charge. The green plot is 0 and increased to the highest, which is the star plot, red star plot. And yeah, well, for state of charge up to 50, you can observe that the rates are similar. It's just that the higher state of charge, at higher state of charge, it occurs a little bit earlier than lower state of charge. And the same happened for the second sample, which is the NMC. You can see the 0 state of charge having low heating rate, and the rest having a higher heating rate. Higher heating rate, but similar. Then comparing the heating rate of those batteries, the two samples, at 100 state of charge, you see the NMC here have the similar heating rate, but it just occurred a little bit earlier than the NCA. And the same happened at 50 degree state of charge as well. But what this indicates is that NMC, the reaction occurred more rapidly, and the maximum heating rate was attained earlier, and then sluggishly reduces the heating rate to maximum point, then cools. Then we look at the physical changes that happened at the battery after the test. And like I said earlier on, the test was repeated 4 times for each state of charge. And you can see for 0 state of charge, we have this line of number of tests, 1, 2, 3, 4. And the green box represents where the battery remained intact after the test. And while the red boxes represent where the battery ruptured after the test during the thermal runaway. And the orange circle represent the region where the part of the battery where the rupture occurred. T stands for the top, and bottom for the bottom side, and S for the side. So most of the, you can see from here that up to 25% state of charge, none of the batteries, none of the NCA ruptured. Then from 50, some of the batteries ruptured, but not in a very regular order, because for some state, at the state of charge, you see some rupturing and ejecting current collectors, while others stayed intact. And we move further, see, for 75 and 100, the same happened. So it didn't show a very regular order. But all I can say here, from 50, the battery could rupture and release content. There's probability that happens, and there's probability it doesn't happen. Then this is the pictures of the battery after test. You can see here, the 0 state of charge, the battery remained intact. This just released some droplets of melted current collector, which is aluminum. Then this ruptured and ejected content. And this ejected content as well, but 100 is still intact. So there's no, it is not very clear what really influences this rupture or being intact, because if this can happen at 50 and 100 is intact, I don't really can explain what happened there. So rupture occurred at no regular order from 50 state of charge and above, but no rupture occurred for all tests below 50. Then considering NMC, you see also from as low as 25, most of the cells ruptured and ejected contents, and most of the test in fact, all of the rupture occurred from the top. And yeah, that's that. Then looking at the pictures also, you see at 25 degree, at 25% charge, the battery ruptured and released almost all of its content. And 75 is intact, 50 is intact, 100 just open the top and release some little quantity of content. So for this particular cell type, as low as 25 degree, it could rupture and release content during thermal runaway. And as low as well as 0, it remains. Probably if test was conducted at maybe 15, we would observe to know what will happen between 0 and 25. But from 25 upward, the chances is quite high that the battery could rupture and release content during thermal runaway. Then the mass lost during thermal runaway when the battery ruptures, it is plotted in percentage, and the red shows that of NMC. And you can see more quantities because from the last slide, we saw the last 2 slides, so that most of the batteries here ruptured from 25 degree high. More quantities of its content was released during the rupture. And that is why you have high percentage loss in mass, up to 50% for as low as 25 state of charge, and then increase with the state of charge up to 100. Then for the NCA, it slowly increased at earlier stage, and then with state of charge up to 75, and then drop. I really repeated this test up to 4 times to figure why this happened, but it repeated, and you can see the error bar showing that chances is quite high that it dropped at 100. I can't really explain why that happened, but from literature, I understand that there is also variation across a given batch of battery. Manufacturer could have some little variation across each cells. So that could be a factor as well. So you can, from here, observe that NMC showed more explosive thermal runaway reaction, resulting in higher loss of masses from about up to 50, from as low as 25%, and while the NCA showed lower explosive reaction. Then that brings us to the last slide, which is the key findings. And on here we observe that under fully charged condition, which represent the worst case scenario when the battery contains highest amount of energy if it is used as directed by the manufacturers, that is excluding the case of overcharge. The onset temperature for SEA is 76 degrees Celsius and 75 for the NMC. The maximum temperature during thermal for SEA is 842 degrees Celsius and 654 for NMC and NCA respect. Sorry, 842 degrees Celsius for NCA and NMC, 650 degrees Celsius for NMC. Again, I need to mention here that the maximum heating capacity of the arc is 314 degrees Celsius, but beyond that temperature limit, the arc does not track the heating of the samples anymore or in the exotherm mode. So chances are that heat might be lost to the environment, to the arc beyond that temperature limit. So I can say that this result is good, but might not represent the actual or very accurate maximum heat that can be released. Yeah. Although the difference might not be significant because at that region, within that region, if we look at the graph, the reaction occurred rapidly and concluded within a very short time. Then NMC, the next point is NMC showed earlier a faster reaction, but attained slightly lower maximum temperature. compared to NCA. Then Rothschild said during TR occurred at 25% state of charge or above that for NMC and 50% state of charge and above for NCA at no regular pattern and mostly from the top. Then NMC showed more aggressive TR event, probably due to high temperature rate, leading to quick gas regeneration and increased pressure. This brings us to the end of this presentation, and I want to thank you for paying attention. I'm happy to take some questions.
Questions?
The state of the lifetime of the battery makes a difference. So if it's a very new battery, or if it's a battery that's been cycled many times, does that make an influence on whether it's likely to encounter thermal runaway?
Yes, from literature, I understand that age of battery is a factor that influences thermal behavior. But in this study, I didn't really look at the influence of aging. I just looked at the battery itself.
There's an older.
The older battery are more likely to undergo thermal runaway at earlier stage at lower temperature. So in designing a heat management system, I think what will happen is that there will be an extra addition to the temperature obtained from this experiment to cover for that. Or maybe another test can be carried out by cycling battery several times to know how that changed with aging of the battery and then put it into consideration.
So, did you do any analysis of what was ejected from the batteries?
Pardon?
You recorded the mass that was lost during the ejection.
Yeah.
Did you monitor what that was, or what the form of that ejection was in terms of different aggressive compounds, or analysis of what compounds were actually ejected?
Yeah, I didn't do detailed analysis, but from visual observation, I saw that some of them, just the dusty particles, which I believe is bond electrolyte and electrode materials. Then the more explosive one ejected visible current collector, which is aluminum foil and the copper foil, and sometimes the mandrel, the pin, the center pin. But I didn't really analyze to say this is the quantity of this and this quantity. I just did visual observation. Yeah.
And so, just a quick final question: are you going to do any tests with LFP cells?
Pardon?
Are you going to do any tests with lithium iron phosphate?
No,
right,
but my colleague really did something on that.
Right, okay.
Yeah.
Okay, thank you.
Thanks for the talk. So was the electrolyte the same in both the NCA and the NMC? And did they have any additives that were, is there in the literature, is there additives that affect the thermal runaway, either suppress the maximum temperature or the heating rate? Is that something that the additives can achieve?
Thank you for the question. I understand that the material used for the electrolyte has some influence on the overall safety of battery. But in this case, I didn't try to compare the materials used in those in the side, except the chemistry of the electrode, which is the NCA and the NMC.
Okay, thanks. And is it 811 as well against?
Pardon?
For the stoichiometry, was it 811 versus?
I believe it might be 811, but that's not stated on the data sheet of the batteries, so it's not very clear. But I just looked at it on the from the angle of their energy capacity.
Yeah, thank you.
Thanks, Solomon, for your presentation. The round of applause. Now we've got Max from the University of Sheffield, talking about sustainable production of porous silicon for lithium-ion battery anodes. Yeah.
So I'm Max Yang, and I joined this. So first I'm going to talk about why silicon for lithium-ion battery. Put one hand here. Why silicon for, I made such a big fuss at the beginning about this, but why silicon for lithium-ion batteries, how it's made, and therefore my research questions. And I'll talk about the baseline cost of making silicon, and then the low temperature method, which is the method I came up with, and how this affects the techno-economic. So silicon has a very high energy density. You can see here, carbon is down here. It's what we're on at the moment for anodes. When it charges, it expands, or the particles of silicon expand and they crack. So you get isolation of these particles that they're not connected to the rest of the battery, so they can't actually store energy anymore. To combat this, you can make silicon porous, and that means that it can expand into its own pore volume and contract without the mechanical stress that causes it to fracture. So it does need to be porous. There are other ways to do it, but this is one of the most promising ways. Silicon markets for the transistor market, so chips, processors, things like that. And it's made by a non-porous route, so the carbothermal reduction. And this requires 2000 degrees Celsius, plus some further processing to make it pure enough to use for chips. But this is actually not good enough for batteries. It's not porous. These two temperatures are well above the melting point of silicon, so the pores get destroyed and you get sintering. So to make it useful for batteries, from here to here is an electrochemical etching, which is it uses a corrosive media, and it's a surface method, which means you can't make it in bulk. Then you can put this into a battery. Not at the industrial scale yet, is the magnesium limit reduction, and this is a one-step process going from silica to porous silicon, hydrochloric acid etching, and it works at 600 to 800 degrees Celsius. So well within the limits of the melting point of silicon, and that's why this is the method I'll be studying. So what does the method look like? Well, in a lab, the powders of silica and magnesium are ground. Heated up in a furnace, but it likes oxygen, and so it won't strip away silica. There's oxygen around it in the atmosphere, so we have to seal the furnace and flow argon through it to make sure there's no oxygen that's been burned from the system. This is then heated up to 650 degrees Celsius, 6 hours usually. Put into 1 mole of hydrochloric acid, which is really mild, and then the magnesium chloride, which is in solution, is filtered off, leaving behind porous silicon. It's a cake, so it's actually a moisture powder with moisture in it. This is dried in the drying oven and then put into a battery. So the issue here is that 650, and I will show you, is quite an uneconomical temperature. The baseline energy cost at the moment, this hasn't been calculated or forecasted, and therefore can the magnesium reduction be carried out at a lower temperature than 650. In fact, I'm going to give a spoiler here. Yes, it can, and I'll show you how it can. Because it can be carried at low temperatures, how does this affect the economics of the process? So how much does it cost to do it at 650 versus the low temperature? So the first question, I selected or I assigned industrial equipment, common industrial equipment. This was done by, I use a selection criteria that you can find in chemical books for equipment design. And these are the equipment that I've chosen. So the powder mixer takes a specific energy consumption. The rotary kiln will be for heat loss, so conduct plus heating up the mass of the kiln and the reactants. And then the impeller would be to stir the powder in acid, and then a dryer to increase the temperature of the moisture, and then evaporate it. So baseline conditions I'm using to build this economic model is 5 degrees C ramp rate per minute ramp rate up to 650 degrees Celsius. And then not really reported consistently in the literature, so I measured this in the lab and I put this into the model. What does this look like? The baseline cost for this baseline condition is about 15 pounds per kilogram. This is at a scale of 3. I changed each of these variables individually, so not in the lab, but just change it in the model. See how much each of these would affect the cost of making silicon. And going from the baseline, changing each of these gets it down to 11 pounds per kilogram. But so that's something that has been achieved in the lab. Well, I have achieved this in the lab. Show you how it can be done. So clearly the temperature needs to go down for the cost to go down. Okay, so I've shown you why the temperature needs to be brought down. I'll show you how the temperature can be brought down now. So the materials chemists among you, this is a solid state reaction. So it's diffusion limited, which means the particle sizes would affect, amongst other things, would affect how quickly. So here it is. I made silica particles using the Sturm method at different sizes. So this is a well-known method. You can make uniform. Silica at 500, 75, and 20 nanometers, and then I reduce them with magnesium at different temperatures. So here on the left, I've got SEM images of particles that have been reduced and washed them. Celsius, nothing has happened to the particles, so no reaction can be seen. But from 550 and above, the SEM images show that something has happened, some reaction. And from on the right, you can see XRD data. The 450 degrees Celsius does not have peaks for silicon. So this is the standard for silicon here. These are the peaks that match up with it. 550 and above, silicon, crystalline silicon is there. 450, no silicon. So 500 nanometers is too big to react at that time. 75 nanometer particles, I found the same thing. So anything above 550 degrees Celsius produces crystalline silicon, but 450 degrees Celsius does not. It might look like there's something happening there. I don't know why this is, but I also gold coat the particles, so that could be what I'm seeing there. But XRD shows that there's no crystalline silicon anyway. This is the more interesting point. 750 degrees Celsius, you can see sintering, so it's really hot. In the sample, throughout the sample, which means crystalline material is present. So there's crystalline silicon here, and to confirm this, the XRD shows peaks for samples reacted. This is in stark contrast to the other two that I've just shown, 500 and 75 nanometers. So there's a threshold here, somewhere between 20 and 75 nanometers, particles will react at 450 degrees Celsius. So silicon is there, I've just shown you it is there, but how much is there? So I did some yield experiments to work out how much silicon was present. Of 550 degrees Celsius, regardless of particle size, reacted to give crystalline silicon, but only the 20 nanometer particles reacted below 550 degrees Celsius, and it went as low as 400, but that's the cutoff point. I did another experiment at 390 and I got 0. Whether this was applicable to other types of silica, not just sugar silica. So I used Celsius, it can still produce a yield as high as 60. This study I did in this paper. So during my PhD, I was fortunate enough to have the opportunity to go to Canada to work with a group also working on the magnesium reduction. It has implications for the techno-economic study that I will present to you next. So they use a method where they go up to 650 degrees Celsius and then hold it there for half an hour Celsius. This is because the reaction is exothermic, so it can sustain its own reaction because it produces heat. This has an interesting implication to the It stays at this low temperature for most of its time, 6 hours. So I showed you the bar graph earlier with the red, and this is how it actually looks like. So to put into context, the one-step reaction to the baseline, at 60% yield costs 50. Increase the yield to 88%. That only brings the cost down to £12. So really, there's not much more improvement can be made. We can achieve. These are all, by the way, I'll show you that next. This is just the model that I'm running and putting variables. Pores will be destroyed and it won't be porous anymore. So to increase it to some fantasy situation, distant to achieve at this point. So ramp rate isn't really the, and the dwell time, this is a very linear. In fact, it is because well, the longer you stay at that temperature, the more the So by bringing the reaction down to makes the biggest difference. So emissions, the yield, and the time it takes. This is the true cost of 380 degrees Celsius, of the 380 degrees. Really, it's staying at 300 for most of its time. 650, it's only there for half an hour. It's a benefit over this method, but it will take longer because in the whole scheme of the process, you have to ramp the temperature up to 650 and then allow it to. So it seems the most obvious option here, but there'll be some scheduling problems that has. That's what I wanted to show. So really, yes, the reduction temperature can be brought down to as low as 450. (41% at 380 degrees Celsius with a yield of roughly 60%. So in terms of the capex, if you have to pay for so the nanoscale, because I'm from a chemical engineering background, I like to go back to the process scale. So the nanoscale, if you make changes there, can really affect the whole process. This is all brown, and also a professor in Mitsubishi at Dalhousie University, hosting my visit to Canada. Thank you, and I'll take any questions.
Did you have any questions?
Thanks for the talk, Max. For the sake of comparison, your baseline scenario, how much of that would you be able to, or like would, as like an industrial person or like process, be able to integrate that into cathode production? Because presumably they need to have high furnaces if you're looking to calcine lithium cobaltate to put into a battery, for example.
Yeah, so there are processes which already exist at high temperatures, and they're made at large batch scales, or actually continuous. So yeah, I can apply the technical model. That's right.
A daft question. So after you've finished processing and produced the porous silicon, does that oxidize immediately if you expose it to air, or is it quite stable in air once it's produced?
Yeah, so that's not a daft question. Or on the bottle, if you buy porous silicon, it says flammable or sensitive to air. But if you just open it up, it doesn't. Nothing happens. Not that I did this, by the way. I didn't do this. So it makes a passivating layer. It's not actually that oxidizable, and then it stops further oxidation of the silicon in the center. But yeah, there will be some oxide formation.
So you pointed out that the nanostructure makes a huge impact on the processing of your material.
Yes.
Whenever you change that nanostructure of the starting materials, does that have any follow-on effect in terms of the nanostructure of what you end up with? And subsequently, if you then incorporate that into a device, would that then change the parameters, the performance of the device?
Yeah. So there's actually nothing in the literature about that correlates exactly pore volume to a specific performance parameter. But yes, the performance of, there are two things: performance of the reactants, the feedstock, would affect the properties of the feedstock would affect the properties of the product, which will then affect the properties of that. There's nothing linking the first two or the second two. And that's something that I will study, hopefully in a postdoc position after this. It's going to be difficult to control one thing at a time, but the key thing with the magnesium limit reduction is that you can use even sand or old glass bottles, and people have done this in literature. So it can make porous silicon from non-porous sources. So you don't necessarily have to use a really expensive silica feedstock for this.
Okay, well, thanks so much, Max. That was a really good presentation. All right, so now we've got the lunch break, and the next session starts at 1:30. So have fun, and see you later.